Hey kids, Charlie Abuso here. Phase 4 chemistry, phase 4 class. This is the end of the notes for phases. Before we get started, once more, what is the vapor pressure? Vapor pressure is an important point, right? We got to know about table H, we got to know about vapor pressure. Vapor pressure is described as that extra pressure that's on the inside of a closed system, like a sealed can or a sealed bottle or a corked flask. In that little space above the liquid, there's air pressure that's going to match the air pressure outside. The vapor pressure is the extra pressure inside that little space caused by the evaporation of the liquid. Now, different liquids evaporate better or less well. And usually when it's hotter, the extra kinetic energy makes for more evaporation than when it's cold. So there's a couple of factors. But the vapor pressure is going to increase with temperature, and certain substances, certain liquids evaporate easier because there's less attraction to themselves. They jump into the gas phase easier. And this can create stress on a system because the extra pressure could cause an explosion. Depends on how the hotter it gets, the more likely it is to blow up. So vapor pressure is on table H for 4 different liquids. Now, on table H, which is what we're looking at here, I got a bunch of points for us to look at, and we're going to describe what the names of these points are or tell what's going on at that. Point 1 on this graph happens to be at a very special point. It's on the dotted line, which is standard pressure, 101.3 kPa, and it's at 100 degrees centigrade, and it's on the water curve. So what do we call what's going on at number 1? That's where water boils at normal temperature. It's called the normal boiling point for water. So point 1 is called the normal boiling point for water. Now, if we happen to ask the question, at point 1, what is ethanoic acid doing? Well, ethanoic acid doesn't boil at standard pressure until point 3. So we're behind or underneath the boiling point. So that would mean that ethanoic acid is a liquid at point 1. What about ethanol? Ethanol at point 1. Well, at standard pressure, it looks like ethanol boils at 80 degrees. At 100 degrees, that means it's a hot gas. Ethanol is a hot gas at point 1. Ethanoic acid is a warm liquid at point 1. Point 2. See what point 2 is? That's way back. That's standard pressure and 55 degrees centigrade. Well, for water, that's kind of a hot liquid. You wouldn't want to drink it. I mean, it's not like coffee hot, but it's uncomfortable hot. But point 2 is right on the curved line for propanone. That's called the normal boiling point for propanone. Propanone boils at a lower temperature. If you had 2 pots and put them both on hot plates, one with propanone, one with water, well, at 55 degrees, the propanone is going to boil away. Well, it's going to start to boil away. The water is just going to be hot in the other pot. Every liquid boils at its own temperature. Point 2 is called the normal boiling point for propanone. Water is just warm there. Point 3. Point 3 is to the right, all the way to the right on the dotted line. So it's a normal temperature. It's a normal pressure there. And that's on the ethanoic acid line. That would be the normal boiling point for ethanoic acid, right? We don't have a point, but on the dotted line, on the ethanol curve, that would be the normal boiling point for ethanol. It would be at approximately 80 degrees and 101.3 kPa. We don't have a dot there, but that would be the normal boiling point for that substance, ethanol. Now, point 4. Point 4 is right on the curve, but it's below normal pressure, right? It looks to be about 80 kPa, and it looks to be about 95 centigrade. So at that point on the curve, water boils at a lower temperature there because there's less pressure. If we have a pot of water, the water molecules stick together, but there's also air banging down on it. The air molecules are banging down, and that holds the water in there. In order to boil, the water needs to jump out of the liquid and into the gas phase all at once, fast. You got to overcome the air pressure on it. But if you have less pressure on it, it's going to be easier for the water to boil. It boils at a lower temperature. So 0.4 actually is a boiling point at the witch's house in Boulder. It's a long story. But in Boulder, Colorado, which is way high in the mountains, there's a lower pressure there. So water boils at a lower temperature. Now, what about 0.5? That's high pressure. At that pressure, which looks to be about 140 kPa, that would be under pretty high pressure. You wouldn't feel comfortable with that with your ears. Your ears would be popping like crazy. With that extra pressure, it looks like water's not going to boil till about 110 centigrade. So that would be the boiling point, maybe deep in a cave. If you're out looking for diamonds in a mine, deep underground, you'd have the whole atmosphere pushing on you, plus that extra air going down into the cave. With really high pressure, that would cause the water to boil at a higher temperature because it would have its normal stickiness, but now with the extra pressure pushing down on it, it'll be harder for the water to boil. So water boils at 100 centigrade, or boils at 110 centigrade, or boils at 95 centigrade, depends on the pressure. 0.6, where the heck is 0.6? That's way at the bottom. Look at that. That's at about 70 centigrade and 30 kPa. Now that is the approximate pressure at the top of Mount Everest. Because you're so high in the mountain, there's so much less atmosphere above you pushing down, the air pressure is really, really low. Water will boil there at 70 degrees. You can heat water up to make tea, but it won't get too hot. It won't get, well, the boiling point for water at that pressure is only 70 centigrade. You can't make it any hotter. Water, because with such little pressure, the water will jump into the gas phase much easier. Now, at any point on this graph, you can only look at one curved line at a time. If you're, let's look at just the water line, the water curve, because that's the one we understand the easiest. If you're behind the curve, anywhere behind the curve, above the dotted line or below that, if you're behind the curve, you're in the liquid phase. If you're in front of the curve, you've already boiled. The curve represents all the boiling points. If you're right on the curve, like points 1, 4, 5, and 6, you are on the boiling point, on the condensation point. You actually have two phases at the same time. Now, the curve labeled water, represents all the boiling points, all of the boiling points at different pressures. Now, what is the boiling point of ethanol at 70 kPa? How are we going to do that? We're going to go up to 70 kPa and slide our finger across till we get to the ethanol line, which curves here, and drop down, and we see that's at 70 degrees. At low pressure, 70 kPa, which is noticeably lower than normal, ethanol will boil at 70 degrees centigrade. This table H tells us what is the boiling point for these four substances at any pressure. It also tells us at any pressure what is the boiling point. And it also would tell us at any point and any pressure of temperature and pressure, are you behind the curve or in front of the curve? If you're behind any one of the curves, that's a liquid. And if you're in front of any of the curves, that would be a gas. Now, what is the boiling point of ethanol at 60 degrees? Say that again. What is the boiling point of ethanol at 60 kPa? So at 60 kPa, I'm going to slide my finger across to ethanol, and this is my dot. See it? I put it right there. I went up from 60 kPa, I slid all the way across to the ethanol line, and I come down, and that temperature is going to be 65. Let's get a good look. See, it worked out exactly right. Of course, it worked out exactly right. What is the boiling point of propanone at 70 kPa? So to do that, you go up to 70 kPa, and I'm going to put a little box around it, and it's going to be 45 degrees centigrade. See what I did there? I went up to 70 kPa, and it slid across to the propanone line and read down what is the temperature there, and that temperature is 45 degrees. What is the boiling point of ethanol at 150? That's pretty high pressure, so let's find 150, and we got to slide it across till we get to ethanol. So let me go slide across till I get to ethanol. I'm going to put a circle around that, and I'm going to check the temperature at the bottom, and it's going to be 90 degrees. See at the top? I slid all the way across to here to the ethanol, and then I went down, and it comes up to be 90 degrees. Table H gets to show you a lot of different things. It shows you all of the boiling points of 4 liquids at any pressure. It tells you whether it's a liquid or a gas at any temperature and any pressure. What's this next one? The boiling point of water at 180 kPa. Now, 180 kPa is pretty dang high. We're going to slide across to the water. I'm going to put a heart there just to make it different, and I'm going to slide down, and it looks like it's going to be 115. So look what I did. I had to go up to 180, and I slide all the way across till I get to the water, and then I have to follow that heart all the way down, and it's going to be 115 degrees centigrade. Think about, what does that mean? If you have water under really high pressure, if you put a pot of water on a Bunsen burner, but in a bell jar with a lot of pressure that you're pushing down on it, water won't boil at 100 degrees. Water boils at 100 degrees at normal pressure. That's when the water's getting bombarded by the air molecules at normal pressure. But at really high pressure pushing down on it, it takes more energy to get the water into the gas phase. What is the boiling point of ethanol at 30 kPa? So at 30 kPa, I gotta go on the left y-axis, 30 kPa, slide across to ethanol, and I guess I'm gonna put a triangle there. And I look down, and it appears to be 50 centigrade. Table H allows you to know the boiling point for any of these 4 substances at any pressure. You just find the pressure and figure out where the curved line is, and you read the temperature at that point. Or at any point, you can know, is any one of these 4 substances a liquid, if it's behind the curve, or if it's a gas, if it's in front of the curve. Okay, Table H tells us, so pick a point, determine if you're in front of the curve or behind the curve. Let me turn the page here. So at normal pressure and 65 degrees. So normal pressure and 65 degrees, 50, 65, that's going to put me right at this spot right here. See that circle I put there? Normal pressure, 65 degrees. That's where my circle is. Relative to water, the water curve is over here. I'm behind the curve. So that makes me liquid, of course, right? At 65 degrees in normal pressure, that's warm water. What about at 90 kPa and 95? We're getting close to the curve. We got to look. So at 90 kPa and 95 degrees, I'm going to put an arrow that shows this dot because this one's really close. See where that is? I'm actually just behind the curve. I'm close, but I'm not on the curve. If I was on the curve, that would be boiling and I'd have gas and liquid, but I'm actually just behind the curve there, and that makes it really hot water, but not quite to the boiling point. You have to be careful, especially when the curves are coming. The curves is kind of curvilicious, and you got to look at this graph with the straight lines. And some of the points like that one are close, but not quite touching. All right. Point 1. What phase is propanone? So I see point 1. You see point 1 right there. Propanone at that particular pressure, and that pressure looks to be about what? I don't know, 85, maybe 90 kPa. Propanone won't boil until about 50 degrees. We're not quite there. So that's going to make, behind the curve, that's going to make propanone a liquid. What? At point 2. Now let's find point 2. That's up in the middle. That's up in the middle. There's 2 questions for question 86. What phase is propanone and what phase is ethanol at point 2? Now at that pressure, which is about 140 kPa, propanone boils at about 65 degrees. We're at about, 75 degrees. So we're in front of the propanone curve, but we're behind the ethanol curve. So in that particular point 2, that makes propanone a gas, but ethanol is still a liquid. Now, how could that be? Well, propanone has a lesser attraction. So at that temperature, it jumps into the gas phase. It's already boiled. And ethanol has more attraction. So it's pretty hot, but it didn't quite get to the boiling point yet. At point 3, that's more on the right side near the bottom. Point 3, what phase is water and what phase is the ethanoic acid? Well, at that pressure, which looks to be about 65 kPa, water boils at a lower temperature than point 3, so water is already boiled away into a gas, but we're behind the ethanoic curve, so water would be a gas there, but ethanoic acid would be still liquid. Point 4, that's more in the center again. That's in the point between ethanol and water. It says, what is the phase of ethanoic acid and what is the phase of ethanol at point 4? Well, we're in front of the ethanol curve, but we're way behind the ethanoic acid curve. So ethanoic acid is still a liquid, but ethanol has already boiled at that pressure. Question 89. At point number 5, point 5 is on the water curve. It's up. What phase is ethanol and what phase is water? Well, at that pressure, which is about 140 kPa, at point 5, ethanol is way in the back. Ethanol is already boiled away. And water, because we're right on the curve, we're going to have both liquid and gas at the same time. We're right on the boiling point, which is also the condensation point. Finally, at point 6, which is near the bottom, point 6 is in front of all of the curves. It's in front of propanone, it's in front of ethanol, it's in front of water, and it's in front of ethanoic acid. At that point, we have all of these substances would be in the gas phase. Table H tells us so many different things. It will tell us what phase, liquid or gas or both, any one of these 4 substances is at any pressure and temperature point on the graph. If you're in front of the curve, you've already boiled into a gas. If you're behind the curve, you're still in the liquid phase. Okay. On a cold day in Vestal, today, look outside, it's cold, there's still snow outside. The air being colder is going to be more dense. The particles are going to move slower, there's going to be weaker and less collisions. The pressure is going to be a little bit on the molecule is going to move slower, so the pressure is going to be a little on the higher side because the air is going to kind of settle down. The pressure, I'm telling you, registers today higher than normal, 1.20 atmospheres. That's 3 significant figures. How are we going to convert this to kilopascals? Give me 2 seconds. Got to get my reference table. And I'm going to go back to where I wrote this. See where I wrote these things right here? I know that 1 atmosphere is normal pressure. 1.2 is higher pressure. How am I going to convert that into kilopascals? Now, you probably can do it a lot of ways. Let me show you the easy way, the 1-step unit conversion math, and we're going to do it. Ready? What's the starting point? 1.20 atmospheres. Now, what is my equality? My equality, which I wrote down, 1 atmosphere is equal to 101.3 kPa. They're equal to each other. So my conversion factor in the middle there, that's equal to 1. Since atmospheres is in the numerator, I put my 1 atmospheres in the denominator, my 101.3 kPa in the numerator. I cancel my atmospheres. I do the math, 3 significant figures. 1.20 atmospheres converts into 122 kilopascals, kPa. All right, I'm not going to do these demos. These demos I've already done. This is the slideshow that I'm going to keep forever, and I would do them now. But I did these demos in the intro videos that you're supposed to watch on Wednesday, the day that we're not together. All right, I used a little plastic cup with a tissue in it, and I turned it upside down and pushed it in the water, and the tissue stayed dry. The reason is that the air, which is invisible, and a lot of people would say, oh, there's nothing there. People who don't know science, people who don't want to think, oh, the air is nothing. No, the air is something. And when you turn the cup upside down in a big tank of water, the water can't touch the tissue because the air is really there, and it pushes against the water and doesn't let the water wet the tissue. The other one I did was I took a full glass of water and put an index card on it and turned it upside down, and the water and the card stuck on the glass. Even though the water wants to come out, the air pressure pushes up on it. Now, I wrote just like magic. It's not magic. This is not magic. I'm not a magician. 100 years ago, I could have made more money being a magician than a chemistry teacher, but now I'm a chemistry teacher. Not magic. Looks like magic to people who don't understand or don't know yet or who haven't thought about it, but pretty cool. I already did those in the video. Check them out. Let's do another math problem. High pressure, 145 kPa. How do we convert this into atmospheres? Well, what's our starting point? 145 kPa over 1. Now, I know, because I wrote it down, you wrote it down too, that 1 atmosphere is equal to 101.3 kPa. So we can make a conversion factor. Since the kPas are in the numerator, I'm going to put 101.3 kPas in the denominator, 1 atmosphere on top. The kPas cancel, got to divide. So 145 kPa can easily be converted into atmospheres. There you go. 1 point on the regions, excuse me. Oh. Yawns are contagious, and nobody's yawning. I don't know where that came from. I don't know who I caught that from. 1 point right there on the regions. Now, 905 millimeters of mercury. We can convert this into kPa also. Our starting point is millimeters of mercury. Put it over 1. Now, I know, because I wrote it down, 760 millimeters of mercury is equal to 101.3 kPa. They're equal, so if we put them in a fraction, it equals 1. Since millimeters is already in the numerator, I'm going to put millimeters in the denominator and 101.3 kPa in the numerator. That conversion factor in the middle equals 1. We're multiplying it by 1. All we're doing is churning or converting the units. Millimeters disappear. This turns into kPa. 905 millimeters of mercury is the same as 121 kPa. Now, on Mount Everest, which is really, 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 really high up, there's a lot lower pressure because you're so high up, there's so much less atmosphere pushing down on you. 31.0 kPa. What's that in atmospheres? Well, I'm catching this yawn for myself. It's chilly in here. It's making me want to take a nap. You can nap soon. We're almost done. 31 kPa over 1. And since I know that 101.3 kPa is the same as 1 atmosphere, I can make a conversion factor. kPa is in the numerator, so I put the kPa in the denominator, and I multiply. This is actually a division problem. The kPas cancel, and with 3 significant figures, I get this many atmospheres. I think we have just a couple more to go. High pressure. Now, when 1 atmosphere is pressing on you, that's normal. When 2 atmospheres presses on you, that's double. This is 2.68 atmospheres. What would that be in pounds per square inch? Well, starting point, 2.6 atmospheres, 2.68 atmospheres. And I know, because I have here and here, 1 atmosphere is the same as 14.7 pounds per square inch. So I can make a conversion factor. Look at it. Put the atmospheres in the denominator so they cancel my starting point, and I turn this into 39.4 psi. Now this is quite a bit higher than normal pressure, but my bike tires would be flat. I told you before, my bike tires, I pump them up to about 90, 95 psi. 39.4 psi, and I sit on the bike, I'd be riding on the rims. It takes a lot of oomph to hold me up. I'm a big man. Now, this is true. I looked it up. The maximum pressure inside an official NBA basketball is 8.5 PSI. Now, that's not very high, right? What would that be in millimeters of mercury? We could figure that out because I know that PSIs are equal to millimeters of mercury. I wrote that down. You wrote it down too. Our starting point, 8.50 pounds per square inch. We're going to convert that into millimeters. How? I know that 14.7 PSI is the same as 760 millimeters of mercury. The PSIs cancel. Now I have to multiply and divide. This one's a little harder. There's numbers on the top and the bottom, and I'm going to divide them. It's going to be 6460 divided by 14.7. So it's going to be 439 kPa. That doesn't make any sense at all. It's not right. Let's see what we got. 8.5 times 760 equals 6460 divided by 14.7, 439 kPa. Oh, look what I did. I know it doesn't make sense. I can't fix it on this. Oh, too bad. I'm going to have to fix this on the other. Let me write on this because this is a mistake. I made a boo-boo. It's not kPa. 439 kPa is high pressure. This is millimeters of mercury. Oops. Right? When you guys hit equal, it doesn't always mean the answer. It means it's time to think. It does equal 439, but normal pressure is 101.3. 439 kPa is really high. 8.5 PSI is under normal. How could I be over normal? That didn't make any sense at all. But it's 439 millimeters of mercury. Sorry about that, right? I made a boo-boo. Oops. I'm going to have to get on that. All right. Kinetic molecular theory. This is it. This is going to explain how gases work. Okay? We'll do this really quick. You don't have to memorize this. You have to understand it. Isn't that a really cool font? Save that from the old days. I can't do that anymore, but I got that and I really like it. This theory is going to explain the motion of particles, molecules. Sometimes they're atoms, right? Here we go. Kinetic molecular theory states, A, gases are made of very small particles called atoms or molecules. That's perfectly true, right? Molecules and atoms. These particles act as if they're small, hard spheres. Not really true. They all have shape, but they act like small, hard spheres in the sense that when they bump into each other, they bounce apart. They don't really get tangled up very much. Occasionally they do, but then they bounce apart. They act like they are small spheres, but they are not spheres. They act like there's no attraction or repulsion. That's also not true. There is attraction and there is repulsion. But if particles of gas attract, that slows them down. And if they repel from each other, that would also slow them down. And if the gas particles kept slowing down over time, that would cool them off. And then they would turn into a liquid. And the air never does that. Gases don't really do this too much, although they could. A small container of gas, if it was cold enough, it would ultimately slow down and turn into a liquid. But the air, it gets hot every day. The sun comes out and re-warms it up. But overall, gases act like there's no attraction or repulsion. Most of the time, gases are gases. How come? Because they act like that. But actually, they do lose a little bit of energy. The particles move very fast and only in straight lines. That's true. They don't spiral. They don't loop-de-loop. They don't go around your head like a little circle. Straight lines like a geometry test. We say the collisions are elastic. That means when the particles hit each other, all of the energy is transferred. None of it is lost. Now, that's an outright lie. When the particles hit each other, some of that energy is turned into heat. Some of it's turned into sound, but the sound is so low you can't hear it because your ears are big and the molecules are little. But of course, when there's collisions, there's a loss of energy. But the loss of energy is very small. And literally every day, the sun comes out, the heat comes on, the gases gets reheated. There is a slight loss of energy, but it's generally so small, it's easily made up for naturally. Collisions result in pressures being exerted. That's true. the more collisions there are, or the stronger the collisions there are, the higher the pressure. And with less collisions or weaker collisions, or both, the pressure would go down. We'll revisit this another time, but this is just interesting to point out. There's something called the kinetic molecular theory that basically explains why gases are gases and how gases stay gases. Now, the last thing it says, the particles of a gas are separated by vast distances from each other compared to their size. The particles are super tiny and the space they take up is great, right? They take up some space, but if you squash the gas down into a liquid, all the air in this room would fit into my pocket. The particles act like they take up a lot of space, but it's kind of like a bull in a big fenced-in yard. The bull itself's not too big, but you don't go in the yard because the bull controls that. And you go anywhere in the yard, the bull's going to come get you, right? The bull itself is not as big as the yard, but the bull controls the whole yard. The air particles that are in this room take up the whole room, but they're really, really small, and there's a lot of space in between. Now, they're zooming around, but they act like they take up a lot more space than they do. There we go. You know what it means on the black screen? I get to stand up and take a bow. We're done with phases. Now, we're going to have some homeworks we got to do. We got a really cool handout, which I have right here. We're going to do, there's more to learn, but there's no more notes. Read the basics, ask some questions. Peace, love, and chemistry. Thanks for coming. Let me get out of here. End. Goodbye, kids.